Good afternoon, everyone. Welcome to the MIT System Design and Management Program Systems Thinking webinar series. My name is Lois Slavin. Excuse me, I'm the SDM Communications Director. I am here with our webmaster, and our speaker for today is a real MIT rock star, Professor Richard de Neufville. He holds appointments in the Engineering Systems Division in the Department of Civil and Environmental Engineering. Before we begin, I'd like to request that if you have any questions, you type them directly into the chat section addressed to all. And with that, I'm going to welcome Professor de Neufville and turn the mic over to him.
Hello, everyone. I have to look direct. You can see me on video. I'm looking directly at the little green dot on my Mac here, and I'm going to pretend you're there. It's a pleasure to be with you. And today the conversation is about flexibility in engineering design, using flexibility to create value. And it relates to it takes off on, wait a second, why is it not advancing here? Because it fell asleep. There, it's all right, thank you very much. I was warned about this. The book on flexibility in engineering design, published by the MIT Press a year and a half ago, and it is available online, and you can get it on an ebook. So the theme for flexibility is that there's a change in paradigm from designing towards a specified set of requirements to the actual conditions using flexibility. And what we find is that flexibility can lead to, not necessarily, but can lead to 20 to 30% increases in expected value. And basically it does this by having a win-win approach. On the one hand, it mitigates the risk, the downside possibilities. That's a win. So less losses is equivalent to more benefits. And at the same time, it opens the opportunities on the upside, again, more win. So those things combined allow for considerable increases in expected value. So here is the outline of the conversation I'd like to have with you over the web. First, I want to put in the context of the standard procedure for designing engineering systems and pointing out why we might need something different, why there's a desire for a change in paradigm. Secondly, I want to talk about the flaw of averages, which gives the mathematical justification for it. And the remarkable thing in this context is that the mathematics of the flaw of averages are really, really very simple. And the only thing that's hard about them is we're not used to thinking in those terms. This lays the basis for the concept of the alternative paradigm, which I want to describe. Then I want to talk about the elements of the analytic procedure, give you an example, and then we can proceed to questions and comments that you might want to have and share with everybody from your extensive experience, and I look forward to learning from you. There's always somebody in the audience who has something valuable to contribute, and I look forward to that opportunity. So what is a standard procedure for the design of engineering systems? It is what has been called, the textbook version is the Systems Engineering V, of which you have one representation here. You can find similar things in various textbooks. It starts with up on the upper left-hand side, somehow there is a definition of the user needs, the requirements, the architectural program. Somebody decides they need an aircraft that can do this or that or the other, or they want an auditorium for 1,000 people, or a sports stadium for 50,000 people, whatever. There is some definition that is typically not driven by engineering, but by some notion of what the client wants or thinks they want. Then that gets broken down into the major components, to subsystems, to the details. So if you're thinking about a a outdoor stadium, for example, you can talk about, well, we have to have the heating, we have to have the bleachers and the grandstand, we have to have the VIP lounges and so forth. So all the pieces get put out to the experts who are doing their piece of it, and then it gets built back up again as the pieces get fit together conceptually or physically, and at the final, at the upper side, the upper right-hand corner, the system is ready to launch or to open, it gets tested, and then it's in operation. That's the traditional aspect of it. And it's been very successful, delivering very complicated things, modern computers, aircraft, all kinds of things. However, let's think about what it's based upon. The implicit assumptions of what I'm calling TSE, Traditional Systems Engineering, is first of all, that somehow the client, the companies, the public know what the needs are. That's quite remarkable. Know what the needs are in terms of, do we need a 50,000 person auditorium, for example, or a stadium? That these requirements are time invariant. We need them now, we need them 5 years from now, we need them 50 years from now. That we can design the whole thing in one process as a coherent whole. That we're only doing one at a time. We do one sports stadium, and then if we go from Boston to San Francisco or to Mexico City, we do it again in a completely designed from scratch. And then finally, that whatever it is that we're building will operate in a stable environment as far as regulations, technologies, demographic, and usage patterns are concerned. However, these assumptions aren't realistic. Do companies know the needs? No. New ones emerge. New sports might come out. We want to use these stadium for concerts, for example. We want to do different things. Are the requirements fixed? No. There'll be new needs, new regulations. American Disabilities Act, for example, required changes. There'll be security requirements, whatever. There are different things that occur. Can the system be designed as a coherent whole and then built in one step? Often not. The owners will add things to it, different facilities, whatever, change the originally built system. Are we designing only one system? Well, probably not. They're likely to be families. Will the system operate in a stable environment as far as regulations, technologies, demographics, and usage patterns are concerned? We can only wish. Basically, what I'd like to leave you at this point is that the assumptions behind the traditional procedures of traditional system engineering are unrealistic. That doesn't mean that traditional systems engineering hasn't been working well. It has been very successful. What's remarkable over the last 50 or 60 years that it's delivered highly complex systems of all sorts. But the issue I'd like to put forward to you is that we can now do better. And we can do better if we step outside the constraints, the box of the assumptions which are unrealistic. We need to think about the problem more largely and more realistically. And the reality is that our plants, our facilities face great uncertainties. We simply do not know what the world is going to be like in 5, 10, 15 years from now in terms of the products, the systems we're deploying. The outcomes are risky, or shall I say uncertain. It's not only on the downside, but it could be on the upside. We could have more demand than we expected. So we need to deal with the reality. That's the proposition I'm putting in front of you. The reality is that we're dealing with uncertainty. So now let me transfer you to the idea of the flaw of averages. And this is very important whenever we're dealing with uncertainty. It's named after, or it was named by, actually, by Sam Savage from Stanford. And it's a pun. It integrates two concepts. One concept is that of a mistake. This is a flaw. The other concept is that of the law of averages. That is generally stated that things balance out on the average. So now let me state what the flaw of average consists of. It consists that if you assume that the evaluation based upon the average or most likely conditions give you the correct answers. And from a simple mathematical point of view, the answer is that if you design, do your analysis, do your evaluation based upon the most likely conditions or the average conditions that you are considering, you will get the wrong evaluation. Therefore, you'll get the wrong ranking of the possible alternatives, and you'll make the wrong choice. It's really as simple as that. Let's look at the mathematics of this. Well, let me say it again in words, is that if we look at the average of all possible outcomes that might occur, the outcomes associated with the different parameters, in terms of market sales of your new product, for example, or the cost of production, or whatever, that if you look at the average of all possible outcomes, it does not equal the value obtained from using the average value of parameters. There's an exception to this if the systems are linear, but I can assure you that except in trivial cases, systems are not linear. So what does all this mean? Let me put it to you in a simple form of mathematics. Really, it's trivial in terms of the mathematics. Don't be scared off of your lunchtime. Here's one illustration of it as a figure. The state of the drunk walking down the busy highway, on average, he's in the middle of the road, and on average, he's alive. In fact, wandering back and forth over it, the average state of the drunk is dead. In other words, if you just look at the average situation, you don't see what would happen when you have excursions, departures from the average. Here it is in mathematics. So let's suppose we have some way to evaluate the system where the evaluation, f of x, is equal to the square root of x plus 2. Very simple, trivial situation. And let's suppose that x could have three different states. 1, 4 of 7 with equal probability. So the average value of x is 1 plus 4 plus 7 divided by 3 is equal to 4. And if we evaluate the system using that average value, we get the function of it at the average is equal to 4. But now, if we think about what f of x could be, if we look at each of the separate values of x, that is 1, 4, 7, we get 3, 4, and square root of 7 plus 2. The average of that, with equal probability, is 4.65. And so the expected value here, the average is 3, 4, and 4.65. The average value of that is 3.88, which is not equal to 4. In short, here is a very simple example which shows you that if you look at the valuation with the average value, you get a different answer than if you look at the average of the actual values that might occur in the various possible states. The bottom line is that unless you look at the distribution of possibilities, unless you look at the uncertainties, overall you get the wrong evaluation for any particular design, and you get the wrong choice of designs overall. That's the flaw of averages. Let me just give you an example of how this works. With a student I've been working with here in the Systems Design and Management program at MIT, we were looking at some reviews of a valuation for a mine in Chile. And we had available to us the spreadsheet on revenues and profits, and we had a deterministic valuation given at the average quality of the ore, the average prices, and we had an evaluation for it, and it looked like a very good investment. But then what we did was to consider that in fact prices went up and down, as they do, and that the quality of the ore varies depending on which block you extract it from, and we got very different answers. So here's the situation as we saw it. So the original valuation, net present value, without the variability, was in millions of dollars, $1,875,000,000. When we did the analysis looking at the possible variations, and for the particular design, which had a particular size of plant there as in terms of million tons a year, we got about 1,072 in terms of millions, and the difference that we had there was 43%. In other words, by not paying attention to the uncertainties, by not recognizing that what the conditions would be if you departed from the averages, you missed the value. The calculations missed the value in very large part. This is the kind of thing that in realistic situations happen. You might ask how this was possible, and the answer is that in such situations, a constrained size of a plant, that if the prices and the quality moved in one way, you were constrained by the capacity and couldn't make use of it, and so you didn't make out on the gains. But if things didn't turn out very well, you got hit with the losses, so you lost on the upside, you lost on the downside, and overall you lost more than 40% of your value by having that situation. So this is the kind of thing we want to avoid. So the practical consequence of the flaw of average is very simple. Because engineering systems are not linear, because any system has constraints, every system has nonlinearities, that unless you work with a distribution of possible situations, you get the wrong answer and a wrong choice of design. Put it in a positive way, the design from a realistically description differs, often greatly, from the design you derive from an average or any single assumption of requirements. And in general this is because the gains when things do go well do not balance out the losses when things do not. Sometimes they're more, sometimes they're less, but they're not the same. It's just like the drunk walking down the center line of the road. That things happen when you have deviations either side of the average, and you have to take them into account. So what's the concept of this? How does it differ from the traditional systems engineering? It has these following elements. First, it recognizes the uncertainty. That is, it's basic to the whole analysis that you recognize that there are variabilities in the situations you'll encounter. The prices of oil may go up, they may go down, there may be new regulations, things happen. It therefore analyzes the possible outcomes of the design. It basically says, let's take a look at what happens if this situation or that combination of situations arise. Then it chooses the system that performs best overall, and basically those situations, those designs, will have embedded into them capabilities to do two things. One is to reduce or eliminate the downside risks. What does that mean? Well, in general, the simple way of viewing this is that if you build your initial system somewhat smaller, or smaller than what you expect eventually that you might want, as if you're less ambitious, you have less to lose, and you cut your downside risks. Now, if you think that things might become more positive, that your product might sell better, you might have more customers for your sports events, you can think about how you can easily expand it, you can build that in, but it's often good to start in a less ambitious way to reduce the possible downside risks. On the other hand, you want to open yourselves up to maximize the upside opportunities. That is, how can you expand the facility or change its function, add functionalities, when, if, and how it seems desirable. And by doing those together, it's fairly easy to get 20 to 30% increases in expected value. So right now, for example, to give you a home-spun example, I am working with a MacBook Air. At one level, it doesn't have very much functionality. It doesn't have a disk drive, for example. But what it does have is it has a number of different types of ports where I can add things to it. So on the one hand, I've made it less ambitious. The manufacturers made it less ambitious. They didn't give me all the things I might need or might eventually think I need. So I have, my expense for it is much less than if it had all the possible functionality that I might have required. But I can, as I discover what I might want to have, I can plug it in and using the ports so it has the flexibility to expand. I can get more memory if I want. I can have disk drives if I want. I can have all other kinds of things that I want if I want to play games or things of that sort. But I can do that only when I want to and only when it gives value to me. So in a very simple way, this particular laptop is smaller, less ambitious than a full functionality one, but gives me all the capabilities eventually if I actually want to have them. So what is the concept overall? The flexible design recognizes future uncertainty. The economy, the technology, the regulation all change. Secondly, the flexible design creates systems easily adaptable to actual futures. That is, it differs fundamentally from the traditional approach. Instead of defining a future and creating a design for that particular future, which, by the way, has very little chance of occurring, that is, if we look at a continuous probability distribution, any particular outcome has a vanishingly small chance of occurring. And the flexible outcome can meet or is designed to adapt to many different possibilities. So it contrasts, the flexible design approach contrasts with the traditional design that often leaves us with plants, operations, poorly suited to the actual conditions and thus inefficient. I'll show that by example with the oil platform, which I'll be discussing in a moment. So what we obtain by using flexible design is a great increase we can obtain for properly organized flexible systems, great increases in expected value. I want to emphasize that. We're talking about expectations. That is, we recognize in the future is uncertain, so we don't know how the system will perform because we don't know the situations under which it will be called upon to perform. So what we do is, on the one hand, we avoid some future downside risks, for example, by building smaller, and that drops the probability of the losses or the downsides. And we build in the capability to profit from new opportunities by taking appropriate actions, expanding the system in size, adding functionality when it's desirable, adapting it in some ways. So those both give us more value on average. And also what we typically observe is we reduce the initial capital expenditures. As if we build more modestly at the beginning, more modestly or less complex at the beginning, we lower the initial costs and therefore lower the present values of future expenditures that we may have because we defer or even avoid them. So the overall what we're getting is higher returns because we avoid the downside risks, higher returns because we profit from new opportunities on average, and we get all this at lower first cost. It's a great formula. Can't beat it with a stick. Let me give you a practical example. In about 5 years ago, over the next following 3 years or so, 3,000 people were coming to work in a 30-story healthcare services corporation building in Chicago. That's basically the Blue Cross building on Millennium Park. And they were doing this while a 20-story addition was building right on top of it. That is, you take a 30-story skyscraper and you double it in size. Now, you can only do that if you had done something right in the first place, and in this case, the structural design, about 20 years ago, with extra steel, utilities, elevator shafts, and so forth, to permit that doubling of the height. In short, the building was created with the flexibility to double in size. This flexibility was only exploited a decade later. So here's the picture. The building is actually built now. I have physical close-up pictures of it, but it doesn't have quite the same impression as this architect's rendering, which shows the initial building and then the completed building. And it's there for you to see, to double-check if you want to. Now, one of the interesting things is, there's a paradox here. The 30-story building with the capacity to expand obviously costs more than the building without the expansion capability. Why does it cost more? Because if you were never going to expand it, you wouldn't have the extra steel, you wouldn't have the extra elevator shafts, and basically you wouldn't have put as much money into it. Yet the amazing thing about this story is that a 30-story building with the capacity to expand saves money. It costs less. Why is this? Well, it is because a fair comparison is between not what you see in front of you and something that would be without the flexibility, but you want to compare it with what a responsible client would have done otherwise. That is, as the Healthcare Services Corporation was thinking about providing for its future, it could either have a reduced size building that it could expand to take care of additional employees and such if it wanted to, or it could have built something larger in the first place, such as a 40-story building. I don't know exactly what they contemplated, but responsibly they would have wanted to do something to provide for the future. So it's either the 30-story, let us say, that could be expanded and take care of the future, or you spent the money up front, not knowing exactly what you'd want, but you'd made some decision to provide extra capacity. And in this case, basically, the 30-story expandable building, flexible design, is less expensive than providing that capacity up front early, and probably not what most desirable, because ultimately, 15 years later on, the company, the corporation, decided to build 57 stories and all, rather than some compromise such as 40 stories that they would have otherwise done. So you want to think about the entire system life and performance, not just whether or not the flexible one has more facilities in it than the inflexible one. You want to compare the flexible design with what you would have otherwise have created. So the flexible design saves money in two ways. One, it lowered the initial capital expenditures compared to the realistic alternative. And secondly, it deferred expansion costs. As we think about the cost of capital being, call it 10%, and you could defer it for 15 years, that's basically like paying something on the order of 10 to 15 cents on the dollar for maybe 20 cents on the dollar for future costs in terms of present values. And furthermore, maybe you didn't defer them, maybe you decide you didn't want to have them in any case, you avoided them because, let's suppose, you wanted to build a different building in the suburbs or in another state or whatever. So the flexible building, the flexible designs often save money. Well, so I painted the picture of what we'd like to show, but what about thinking about how do we actually go about doing it? What's the procedure? I'd like to think about it in 4 steps. The first step is to recognize the uncertainty. That's fundamental. Not just to recognize it is there, but to somehow characterize it. What does it look like? What are the uncertainties that we're facing? How do we think about them? So that puts us in a space which is very different, because it says, it doesn't try to focus on what will be the future, some kind of demand forecasting which specifies the future, which, by the way, is highly unlikely to actually be seen, but to think about what are the various possibilities. Secondly, recognizing those, we want to see how the system would perform for the range of scenarios. I put down here we simulate them as we estimate them, but typically what we do, in fact, is Monte Carlo simulation, seeing how the system will perform with different situations. High demand, low demand, new technology, new rules. How does it perform? What's going to affect it? Then we want to say that we want to evaluate the system. But this evaluation is going to be slightly different than if we're thinking about the traditional evaluation where we rank them by some kind of number. For example, their present value if we're looking about economic terms. Because what we're going to see is we're comparing systems which have a distribution of possibilities. Sometimes they perform very well because the situations are favorable. Sometimes they perform not so well because the situations aren't unfavorable. We don't know. We're trying to cover our bases. But one number is not enough to describe a distribution. We need to think about the performance over the range. We need to compare distributions. I personally am going to suggest to you, by example, that we can look at the shapes of these with what is called a target curve, but we can also think about describing them by means of tables of performance, high performance, low performance, average performance, standard deviation performance. Finally, we need to think about, for successful flexible design, we need to think about implementation. So let me go back to the buildings here that I'm showing about. In order to be able to double the size of this building 15 years later, one of the things that looks maybe minor, but was part to illustrate the kind of thing that needs to be thought of, you need to be able to double the size, you need to be able to think about, well, how am I going to get the steel up there? That is, Chicago is sometimes known as the Windy City, and in order to build an extra 15 stories, an extra 27 stories on top, you need to hoist huge girders up, swaying in the wind, basically, past all the windows of people working on the lower stories. So you had to give a great deal of thought to how you'd actually go about doing that. And my understanding is they did it very successfully. But you had to pre-plan it. Another thing is that this building, like others, has a lot of glass, but it also has some granite facings on it, stone facings on it. And they didn't want their building to look silly, that is to have one color of facing on the bottom half and another color on the top half. So one of the things they had to do was to make arrangements with the quarries that if they ever wanted to expand it, that they had a block of material reserved for them so that if they ever needed it, they could get the same color. Thank you very much. So what I'm trying to emphasize is that to have a flexible design, you need to not only have the availability of it, being able to use it in principle, you have to go through and think through exactly how you'd go about implementing the design later on. That is, you have to think about the design not as something you build once, launch, and then let somebody else take care of. You have to think about the design over the lifetime that you are, for which you are creating it, so that you will be able to exploit your flexibilities to adapt it over time. So let me now go from the 4 steps of the procedure to talk about them a little bit more in detail. In terms of the recognition of uncertainties, we want to go through a process which tries to estimate what is happening. So we look at past experience that we might have, we look at the record, we look at how well we have or have not been able to forecast what's happening, what's the deviations of it. In other words, we inform ourselves by looking over past history. But, of course, that isn't enough when there are new situations that may occur. So we also want to bring in judgment about important, possible, but perhaps unprecedented scenarios. For example, there may be new environmental regulations. There may be technological change. There may be commercial changes, mergers of competitors, for example. So what I want to emphasize here, when we think about uncertainty, this is not strictly a mathematical exercise. We have to think about the various scenarios that may occur. We have to think about which ones might affect us the most, so that the builders of the Healthcare Services Corporation building in Chicago, when they were thinking about what their future was going to be, they had to think about the future of the organization of healthcare, where they're going to be in Chicago, where they're going to merge with other companies, what would be permitted, what would not be permitted, where they were going to be sited. All these things that were changing then and are very much changing now, and they had to think about that. And it was not just a statistical exercise of extrapolation trends in the past, however sophisticated. So this is should be a thoughtful process. We can talk more about this in the question period, should you think of it. One of the issues in this, I might mention, that if you think about the number of possibilities, they're immense. So if I thought about the copper mine, as I alluded to when I discussed the law of averages, if I thought about it over 20 years and it had 3 different states every year in terms of the copper price, which influences the value, and I thought about all the possible combinations, it's an absolutely enormous number. So I need to have some kind of way of examining this in an efficient way, and our optimization procedures aren't really up to that at this point. So it justifies the simulation approach. And what we also need is we need to be able to evaluate things fairly quickly. We can't have a complete model of everything that might happen. So what we use is this notion of screening models. That is, simplified model of a situation that can run quickly, in minutes, instead of hours or a day. I'll talk about this in the example of the oil platform. So we then simulate the system performance in the range of scenarios, and we use these mid-fidelity, crude if you want, models, not for detailed analysis, but to identify sweet spots that we can then look at for detailed analysis. So the evaluation, we're looking at distributions, as I mentioned before, and we want to think about not just what would happen on average, but we want to think about the extremes, we want to think about the capital expenditures. And we need to have the implementation. Let me try to put all this into context by looking at this example of working on a deep water oil platform. This is the kind of thing I'm talking about. This is a platform called Andrew in the North Sea. This is actually a relatively small version of it. It cost about $2 billion. The details of this case is it's in deep water, and the design team for this platform was using the traditional approach, which they used a value of oil, a price of oil is given to them by their board of directors, and they looked at the most likely, or more precise, the median value of the amount of oil that was there, and focused on having a single large facility. Now, they designed it, in other words, for a very specific situation of one price of oil and one design. Now, as you may know from personal experience, the price of oil is highly volatile. Over the last 15 years, it's gone from about $150 to $15 at various times, and the amount of oil that's available to be recovered is very difficult to determine at the design stage, because you won't know it until you've actually sunk some wells and try to suck some of it out, depending upon the pressure and the geology of the field. This is just a quick view of how the prices of oil have changed over time, and you can see the big variability. And these are examples of the estimates of the quantity of oil here, and these are from BP and from the North Sea. So on the example on the right, going over time from left to right, from the initial exploration to the appraisal phase, you can see that the one on the left, the P50, the most likely one, is far, far above, twice the size of what was actually determined to exist later on. And if you design for the P50, you'd have something which was much too large for the actual situation. On the other hand, with the other one, on the right-hand side, if you design for the P50, you'd be about half the size of what was actually needed later on. This is just an illustration of the kinds of things that happen. And as you can see, the uncertainty does not narrow down quickly into an average value. It jumps all around. This is very typical of actual situations. So what is a flexible approach to design here? Well, instead of having a single large platform, we can think about having smaller initial platforms that can be expanded, or the capacity can be expanded when and as needed. That is, we can locate them in different places, we can build them up when we want them. And by building them smaller, we have much less invested at the beginning. That is, until we actually know what's down there, we haven't built a big, large platform. And on the other hand, if the quantity is high and the prices are good, we can expand larger than we'd originally done it. So we can just think in terms of the size of it. A fleet of possible small platforms, or one big one. One inflexible one, or capacity able to roll out over time. More subtly, perhaps, we can also think about how we tie the pipes feeding the platforms together, and how we have these interconnections to be able to manage the flows between the various locations more flexibly and use the capacity better, and basically get more easily as we go along. So there was an obvious one in terms of the size, and there was a more subtle one, but both give you the ability to manage the situation as it actually develops. And the cumulative effect is that comparing the two designs, the fixed design is subject to large losses if the extractable quantity of oil is low and the price is low. And in fact, this is what has happened quite frequently in various designs, is that the platforms might be successful insofar as they suck oil and they don't have accidents happening to them, but financially, many of them designed for the P50 are over-designed for what's actually there. And on the other hand, the fixed design cannot easily take advantage of better opportunities if the reservoirs are larger and more productive than their best estimate. And on the contrary, the flexible design improves because it has much lower exposure to losses, and the ability to take advantage of the good situations. So it moves the cumulative distributions of outcomes much higher. This is the kind of graph that we presented to it, and let me take a few moments to explain it before ending the discussion. So the pink curves, these are called the target curves, or also the value at risk curves. The pink curves represent the distribution, the cumulative distribution of possibilities for the initial strategies, basically the one large platform. And you can see in the lower left-hand side, minus 100, minus 50, these are all normalized to the original design, could lead to very large losses, minus 60, minus 80, something like that. On the other hand, they could go to very large designs, and the original one has an expected value, an average value centered on 100, that vertical line going up and down in the curve. And as you can see, this is actually measured in, centered around a couple $1 billion, by the way, just to give you an order of magnitude, that you could do very well, but you could also lose a lot, and you could also, well, it was a good project on average. But we went through various designs, the team I was working with and I went through various designs, and representing by those other lines, and the black one, turned out to be our most desirable one. And as you can see, its lower left-hand side is in the positive range. It wasn't going to lose money. That wasn't our expectation, because built small, there was less on the line, and you were pretty sure that it would be able to extract oil and pay for itself very nicely. And on the other hand, because it has the flexibility of the subsea tiebacks, and by able to expand its size in modules, it could perform much better on average. And in this one, we did it for a major company. The normalized on 100, its average value was that vertical dashed black line, which was about 78% better than the original design. And if I had just 1/100 of 1% of this, I would probably own an island in the Caribbean and be living in a Mac mansion now. I just wish that our advice had some kind of royalty stake in it. But what I'm suggesting here is the kind of thing we observe very often, is that we redistribute the possibilities, cutting the downside, that is the left-hand side of the curve that was in the red for the original designs, adding on the upside, going over, increasing the black side, the positive side of the ledger, and having a much greater overall capacity at the end. So the bottom line improvement is that the expected increases value of about 78%, lowered the initial capital expenditure about 20%, and as near as we can determine, these were the real results. So the flexible design is more realistic in terms of dealing with the situations that it might actually be, and profitable. So the summary of the entire thing is that flexible thinking can greatly increase expected value from projects. It is a new paradigm, not the traditional approach. And because of this, I think that it's a must for future system designers and managers. Thank you very much for your attention. Here is another picture of these kind of platforms, just to give you an impression of it. And I'm going to leave you with a reminder of the book that my colleague Stefan Schultes from Cambridge University, the University of Cambridge, and I put together. And it's available from the MIT Press. Thank you very much. And now I think I might have some questions that will be given to me. I really appreciate the chance to talk with you.
Okay. Professor de Neufville, thank you very much. And you have several questions, several interesting questions that have been submitted by folks here. Okay, the first one is from Enrique Chada. how does this approach work when needs are unknown and the solution unknown?
¿Qué tal, Enrique? Thank you very much for dialing in. I always enjoy talking with you in person also. So, at one level, of course, we don't know what the future is, but we, of course, have some ideas. So that thinking about almost anything, whether it's an airport or a cement factory or a copper mine, we know something about it, but we don't know exactly how big it should be or what we're supposed to be doing. So that part of what we should be doing is thinking about, well, what might we expect? Does it look profitable on average or worthwhile? Because, of course, it's not always profit that drives us. We're thinking about designing hospital systems that may not be profitable in the financial sense, but it may be successful in terms of reducing disease or reducing mortality, which is not financially measured. So we try to anticipate the range of possibilities and build up a solution slowly. The more uncertain we are, the more natural it is to be more flexible and more tentative about it. I mean, one of the things about flexibility is that flexibility derives value from the uncertain. It's like insurance. And in fact, insurance is a form of flexibility. That is, if you're absolutely sure you won't have an accident, no sense in buying accident insurance. What makes insurance valuable is exactly the possibility that you might have a problem. Think about having a spare tire in your car. If you are driving around town only, you might not have much of a tire. You might have a little donut tire that can take you 20 miles because all you need to do is get to some gas station and there are a lot of them around. On the other hand, if you're crossing the Sahara, where things are very uncertain, you might want to have 4 spare tires and spend a lot of money on it to have them and drive them around. But the greater the risk, the more flexibility is valuable. And in any case, you start tentative, not to close off possibilities, and not to overcommit. I hope that's helpful. I'll be glad to talk to you some more anytime, Enrique.
Okay, the next question is, hold on. We have so many questions coming in, the screen keeps refreshing. From Jerry McNeish, how can the flexible design know what future functions might be desirable?
Well, it's interesting. I was just talking about this this morning in some discussions with an IT developer, where we simply do not know exactly what kind of information we might be dealing with. Think about sensors throughout the city to read traffic and things of the sort. One of the ways you want to design is to think about the range of possibilities and how you might have interfaces which would connect to things. So, for example, I, and you probably too, have USB and other ports on your computer, and who knows what might plug into them. But what we do in these cases is to allow a system which has the capability of permitting a range of functionalities associated with it. Same thing with a smartphone. The interesting thing about whether it's Android or an iPhone is that the people who developed these platforms had no idea of all the possible apps that you could be in there, but they designed it so that it would be fairly easy to install different kinds. So some people have chess games on them, other people have levels, subway information systems, etc. You do your best. But what you do not do is think that you know the answers and design just for what you think you know, because you're quite likely to be inaccurate in your assumptions.
Okay. The next question is from Duke Nguyen. Sorry if I'm mispronouncing your name. And the question is, how can one reflect flexibility in a contract between the owner and the design builder?
Well, this can be done in a variety of ways, and it has been done in a variety of ways. So, for example, if we're talking about the George Washington Bridge connecting New Jersey and New York was originally built with one level, but it was the client, the predecessor of the New York Port Authority, I think it was, basically agreed to pay a little bit extra in some ways for the possibility of doubling the deck, putting a double deck on it later on, and that was the understanding the client wanted to buy that flexibility to install that second deck, which was then built 30 or 40 years after the original design. I'm not sure exactly. So it is part of a conversation between the client and the designer as to what should go into it. And it is clearly a collaborative thing that needs to go forward. And there are a variety of ways of doing it.
From Guillaume Dumas, what are the key parameters for defining the trade-off between control and flexibility?
Bonjour, Guillaume. I suppose you are French speaking. Well, it's not exactly sure how to interpret your question, because I think this depends upon the kind of client that you're dealing with and the objectives of the client. What you are really trying to explore with the client is what are they trying to achieve, and what are the risks, the uncertainties which they're faced, and how you'd like to deal with them. So imagine yourself in some ways dealing with a client who is looking to buy insurance, an insurance package for their family and their home and so forth. You'd like to address the concerns, maybe I want house insurance, burglary insurance, flood insurance maybe, I don't know. So you'd like to think about that and create a package that makes sense for the client and that addresses the various possibilities that might occur. So this is, I think that the answer depends upon the situation, but it's an ongoing recognition that there is uncertainty. It is effective to recognize it and look for solutions.
Okay, this is the last question we'll have time for today. However, I'd like you to know that we will be sending you a link by the end of this week to Professor de Neufville's recording and his slides. And we will also include his email address in case you would like to address your questions directly to him.
A question, Lois.
Yes.
Do you have the recording of the questions? Because I'm happy to answer the written ones, not right after this, but during the week, if that's okay.
I do. Yes, I'll be happy to send that to you.
So people who have written in their questions, I'll be happy to do my best to answer. And as a general statement here, one of the ongoing projects of my colleagues and myself is to try to think about how to apply these possibilities, these principles, if you will, in different contexts. People were asking me just the preceding question about the key parameters. If you are constructing a building, they're going to be different than if you are designing an aircraft or a ship or an information system. So the approach in detail for the different fields is likely to be different. So that's why I'm hedging my answers a bit, because it's not a definitive answer for all situations. But I have one last question, so read it to me a little.
Okay.
Hit me. Don't you dare. But hit me with a question.
For those of you who know Professor de Neufville, you're familiar with his sense of humor. From Jose Fernandez, where do we apply flexibility, at the functional level or at the quality attributes level?
Well, thank you very much, Jose, for that question. So, for example, the functional level, and one way to do it is you think of your system as a platform to which you can add functions. So my Mac in front of me has these ports, as you know, and I can add different functions that the designers may never contemplate. Just like my iPhone or yours or your Android, your smartphone, has apps on it that the designers of the phone itself had no thought of originally, so that you create possibilities. But this also leads to the qualities. You may say, well, depending on how you define qualities, but maybe I would like to design my system so I could start off with a high end, but maybe I'd like to be able to have a cheaper version of it because I want it for grade schools, for example. I want it for different contexts, so that you can think about how you can not only upgrade, but how you can downgrade them for have a different intersection of quality and price for what you're doing. So the ability to adapt to the range of circumstances is what you're looking for, and there are many ways to treat it, depending on the product or the system. Thank you, everybody, for a wonderful chance to be with you, and I will do my best to respond to your comments when I see them from Lois. Thank you so much.
And thank you all for attending. Before we sign off, two things. Number one is, please mark your calendar. The next webinar will be on May 6th. That's Monday from noon to 1 p.m. The title is Technical Debt in Large Systems, Understanding the Cost of Complexity in Software, and that will be presented by Dr. Daniel Sturdivant. The second item is, please, if you're interested in this, don't forget Professor de Neufville's book, Flexibility in Engineering Design. We'll include a link to that in the follow-up email as well. Thanks, everyone. Have a great rest of the day.